In today's lesson, we're going to talk about experimental and theoretical probability. This is lesson 10-5 and 10-6. Your objectives for today are to determine the experimental probability of an event, determine the theoretical probability of an event, and the complement, and identify situations for which the law of large numbers applies. We're going to look at some terms before we look at our first example. You do not have to write these down. Your first term here is experiment, an activity involving chance. Trial, each repetition or observation of an experiment. Outcome, each possible result of an experiment. Sample space, the set of all possible outcomes of an experiment. And event, an outcome or set of outcomes in an experiment. All right, so an example of some of those things, an experiment would be rolling a number cube or a die, tossing a coin, or spinning a game spinner. Sample space, the set of all possible outcomes of an experiment, is like all the numbers that you could possibly roll on the number cube or die, the heads or tails of a coin, and then the different colors on the spinner. Probability is a measure of how likely an event is to occur. All right, I want you to write down the definition for probability. It says probability is the measure of how likely an event is to occur. So I do want you to write that down. You do not have to write down the rest of the information there, but just pay attention. So I tell you that it can be written as a fraction from 0 to 1, a decimal from 0 to 1, a percent from 0% to 100%. And again, on this slide, I need you to get down that probability is the measure of how likely an event is to occur, and have that down before you move on. Theoretical probability, and I want you to write what's here in the blue box. Theoretical probability, the theoretical probability of an event, is the ratio of the number of ways that event can occur to the total number of equally likely outcomes. So write this down in the blue box. Theoretical probability equals, and on top of the fraction you have the number of ways the event can occur, and on the bottom you have total number of equally likely outcomes. Make sure that you have that down before you move on. And we're going to look at this in practice in just a minute, so it's going to make a lot more sense. You can perform an experiment to estimate the probability of an event. The experimental probability of an event is the ratio of the number of times the event occurs to the number of trials. The more trials performed, the more accurate the estimate will be. Write what's in the blue box here, experimental probability, number of times the event occurs over the total number of trials. All right, so make sure that you have written down what's in the blue box here before you move on. All right, for number 1, we're going to be dealing with the theoretical probability. It says, determine the theoretical probability of the spinner landing on orange. Write the probability as a fraction, as a decimal, and as a percent. So theoretical probability means that we're not actually dealing with specific experimental data. We haven't actually spun the spinner, but we can look at the spinner and observe its characteristics, and based on what we see about this spinner, we can say, in theory, if we were to spin the spinner, this is what might happen. So it's asking us to write the probability as a fraction, as a decimal, and as a percent. The probability of the spinner landing on orange. You can see here, this is the orange section of the spinner. There are a grand total of 1, 2, 3, 4, 5, 6 sections of this spinner, and only one of those 6 equally sized sections is orange. So the probability that orange will be the outcome, that's what we want to know. The probability of the spinner landing on orange when there are a total of 6 sections and only one of them is orange is 1 of 6. So we write that as a fraction, 1 over 6, because there are 6 sections and orange is only one of those sections. If we were to write that as a decimal, because it said write it as a fraction and then as a decimal, we can simply convert it to a decimal by typing in 1 divided by 6 in our calculator, and it's going to give us 0.1 with 6 repeating, thus the bar over the 6. And then we need to write it as a percent. So as a percent, we're going to multiply it by 100, and it's going to give us 16.7% because we're going to round up to 0.7 from that repeating 6 there. You need to have everything in black here written down. If you want to draw the spinner over here and just show that it's in 6 equal parts and that they are each different color, you don't have to color it or anything like that. But if you want to draw that so when you go back and look at this later it makes more sense to you, that's fine. We're not going to require you to do that. We're going to go ahead and look at part B of number 1. Now, the last part A was theoretical probability. So in theory, if we spun the wheel, where would it land? Part B is dealing with experimental probability. So that's why we have a table here.
Yes.
You have a parent up here.
Okay, so we're dealing with experimental probability here. We have the spinner, and the spinner has been spun, and we have a table of data. So you do actually need to write the table of data. I need you to write the table, red, orange, yellow, purple, green, blue, and write the frequency. For red, it was 11 times. It landed on red. Orange, it was 8, yellow, 5, purple, 7, green, 10, and blue, 9. So this experiment has been conducted, and we have to determine the experimental probability of the spinner landing on orange. So we're going to write the probability again as a fraction, a decimal, and as a percent. So we're going to look at the percentage of times it's landed on orange. It has landed on orange with a frequency of 8. So 8 times out of the times it's been spun, it has landed on orange. How many times has it been spun? We have to add up the frequency for every different color. So you have here 11, 8, 5, 7, 10, and 9. That equals 50. So the number of trials is on the bottom of the fraction, and the number of times the event has occurred, which for us in orange has been 8, is on the top. So we're going to write that as a fraction as 8 over 50. Very simply, we're going to convert that to a decimal by dividing 8 divided by 50, and that's going to give us, we reduced it to 4 over 25. Then we're going to divide 4 divided by 25, and that's going to give us 0.16. We're going to convert that to a percent by multiplying it by 100, and it's going to give us 16%. So the probability was 16%. The law of large numbers says as the number of trials increases, the experimental probability gets closer to the theoretical probability. What this means is look at what we just did. We have our experimental probability here and our theoretical probability here. The more times we experiment with our spinner, the more likely it is that we will end up getting closer to the theoretical probability. So right here, our theoretical probability was 16.7%, or 1 in 6, because that orange takes up one piece of that pie. Here, in the experiment, our results came out to be 16%, the chances of it landing on orange, which is incredibly close to 16.7. Now, if we had only spun the spinner 5 or 6 times, chances are our experimental probability would not have been near as close as this to the theoretical probability. But what we're saying here is the law of large numbers. The more times we experiment, the more times we spin, the more likely it is that this experimental probability is going to end up almost matching or actually matching our theoretical probability. The complement of an event is all the outcomes in the sample space that are not included in the event. So it's everything else. The sum of the probabilities of the event and its complement is 1 or 100%, because the event will either happen or not happen. So write this down. P, which stands for probability, by the way, of an event, plus P times the complement of the event equals 1. So again, the probability of the event happening plus the probability of the event not happening is going to come out to be equal to 1, or 100%. So this is what we want to see happen, like spinning orange on the spinner, and this is spinning anything other than orange. So let's look at that. We're determining the experimental probability of the spinner not landing on orange, so anything other than orange. And we're going to write the probability as a fraction, as a decimal, and as a percent. So again, we've determined that there are 50 trials here in our experiment. Everything other than orange. So we're going to add up all of the numbers, 11, 5, 7, 10, and 9, for everything other than orange. And that's 42. So 42 out of 50 trials, it landed on a color other than orange. So we're going to write that as a fraction, 42 over 50. We're going to reduce that down to 21 over 25. We're going to divide that out. 21 divided by 25 is going to give us 0.84. We're going to write that as a percentage by multiplying it by 100, and it's going to give us 84%. Now, we have 84% chance that it's going to land on something other than orange, and we had a 16% chance that it was going to land on orange, so you have 16% and to 84%, and when you add those, you have your fraction 4 over 25 plus 81 over 20, plus 21 over 25, that equals 1. 0.16 plus 0.84. Add those together, the probability of orange, the probability of something other than orange, you get 1. 16% plus 84%, and you get 100%. So you can see here that it equals 100 every time, or 1. All right, number 2 says determine the theoretical probability of rolling an 11 on this 12-sided die. Write the probability as a fraction, as a decimal, and as a percent, just as we've been doing. So theoretical probability means that no experiment has occurred at this point in time. And we're talking in theory, if I were to roll this die that I'm not even holding in my hand, what is the chance I would roll an 11? It has 12 sides. So out of 12 possible sides, there is one side that is an 11. So in theory, it's going to occur one time in 12 that I will roll an 11 on this 12-sided die. So 1 divided by 12, when I divide that out as a decimal, I'm going to get 0.083 repeating. I'm going to multiply that by 100 to change it to a percent, and I'm going to get 8.3%. So there's an 8.3% chance that I'm going to roll an 11 on this 12-sided die in theory. Make sure that you have down what's in black before you move on. All right, an experiment consisted of rolling the die. So now we've moved on to experimental probability. A frequency table was created, and I want you to copy down this frequency table. It says outcome, and you have outcomes 1 through 12. I want you to list them. Frequency. 3, 1, 0, 5, 6, 2, 1, 3, 2, 5, 3, and 4. What this means is that 3 times that the die was rolled, it landed on 1. 1 time it landed on 2. 0 times it landed on the number 3. 5 it landed on 4. 6 times it landed on the number 5, and so on and so forth. Make sure that you have that table copied down before you move on. All right, so I want to know now the experimental probability of rolling an 11 on the die. I have to determine how many times this experiment was conducted. How many times did we roll the die? So to do that, I have to add up all of my frequency numbers here, and when I add all those up, I'm going to get 35. So the total number of trials, the total number of times the die was rolled is 35. And now I have to see how many times it landed on the number 11, because again, I'm looking at the experimental probability of it landing on 11. So it landed 3 out of 35 times it landed on the number 11. So I'm going to write that as a fraction, 3 over 35. When I divide that out, 3 divided by 35, it's going to give me, and this is approximately equal, so that's showing me that I've rounded here, 0.086. Now to write that as a percentage, I have to multiply it by 100, and that's going to give me 8.6%. So that's approximately equal to 8.6%. So my experimental probability of rolling 11 on this 12-sided die is approximately 8.6%. So let's look at our law of large numbers. As the number of trials increases, the experimental probability gets closer to the theoretical probability. So here I have 35 trials, and my experimental probability is 8.6. My theoretical probability is 8.3. The two are very close to each other. If I were to do even more trials, chances are that this experimental probability would come even closer to my theoretical probability. So now we're going to look at the complement of the event, the chances that it's going to be anything other than the number 11 when I roll that 12-sided die. So I have to go back again and look at my number of trials, and this is the same table you've already copied down. Anything other than 11, the probability of it being not 11. So again, I know I have 35 trials, and I've got to add up all of my other trials, or I can take the 35 and just subtract the 3. Because I know that 3 out of those 35 times it ended up on 11. So I can just take 35 minus 3, which is going to give me 32. So I'm going to write the number of times the event occurred, which is 32, that it landed on anything other than 11, divided by 35. And that's going to give me approximately 0.914. When I multiply that by 100 to turn it into a percentage, it's going to give me 91.4%. So now I can go back and add up my 91.4% to my 8.6%, and it's going to give me 100%. When I look at that as a fraction, it's 3 over 35 plus 32 over 35 equals 1. I want you to write that down. 0.086 plus 0.914 equals 1. I want you to write that down. This you should have already written down. If you didn't write it down on the last slide, write it down here. 8.6% plus 9.4% again gives me 100%. There's a 100% chance it's going to land on something. One of the numbers on the die. Okay. The next example we're going to look at says a bag of marbles contains, a bag of marbles contains 4 red marbles. So I want you to write 4 red. 3 orange marbles. I want you to write 3 orange. 7 green marbles. I want you to write 7 green. And 1 blue marble. I want you to write 1 blue. So you should have 4 red, 3 orange, 7 green, and 1 blue. The question says to determine the theoretical probability of randomly choosing a red marble from the bag. Write the probability as a fraction, as a decimal, and as a percent. All right, so we want to know what the probability is of us randomly choosing a red marble. There are 4 red marbles. We have to determine first how many marbles there are total in the bag. So we have to add our 4, 3, 7, and 1. And that's going to tell us that there are 15 marbles in the back, and there are 4 red marbles, so there is a chance of what we're going to say 4, the number of ways the event can occur, 4, because there are 4 red marbles in the bag, over 15, because there are a total of 15 marbles. So write 4 over 15 as a fraction. Now we're going to divide that out to write it as a decimal. 4 divided by 15 is going to give us 0.26 repeating, which is approximately equal to, when multiplied by 100, 26.7% chance that it's going to be a red marble when we pull a marble randomly from the bag. Again, theoretically, meaning we're not actually experimenting with the marbles in the bag at this point in time. Sorry. Make sure that you have that down before you move on. In black here. Now I want you to copy the table of experimental data. Red equals 6, green 5, orange 5, green 11, and blue 3. So red 6, orange 5, green 11, and blue 3. So now we're going to look at the experimental probability of choosing red. So the experiment has been conducted. We're going to add up our number of outcomes to find our number of trials. So our number of outcomes, 6 plus 5 plus 11 plus 3, gives us 25. So the experiment has been conducted 25 times. 25 marbles have been pulled from the bag. And the number of times a red marble has been pulled out is 6. So we're going to write that as 6 over 25 as a fraction. We're going to divide to turn that into a decimal, 0.24. We're going to multiply by 100 to turn it into percent, and it's going to give us 24%. So in our experiment, 24% of the time, a red marble was pulled from the bag. Make sure you have down what's in black here in the table. Now we're going to look at the complement, the probability that something other than red, or not red, was pulled from the bag. So again, we have 25 trials according to our table that we just copied down. And the number of times the event occurs that something other than red was pulled from the bag. This is not correct down here. This 6 is incorrect. We have to add up the number of anything other than red. So we have 5 plus 11 plus 3, which is going to give us 19. So we're going to write that as a fraction, 19 over 25. We're going to divide that out to make it a decimal, 0.76. We're going to multiply it by 100 to turn it into a percent. It's going to give us 76%. So there's a 76% chance in our experiment that we pulled, in our experiment, 76% of the time, we pulled something other than a red marble out of the bag. So here you have part B and C to number 3. The probability of it being red was 24%. The probability of it being anything other than red was 76%. And when I add the 24 plus 76, I get 100%. When I add my fractions, I get 1. My decimals, I get 1. And my percentages, I get 100. So make sure that you copy down what's in blue here before you move on. This is the last example. I'm going to have you copy down your homework. This is your homework assignment for this lesson. Lesson 10-5 and 10-6. There are 14 problems. Page 740, number 8 through 10, 18 to 20, and 22. And then page 747, 2 through 8, evens only, and 23 through 25. This is the end of your video. Thank you for watching.